Look up at the night sky. See those stars scattered across the darkness? You're looking at our home galaxy, the Milky Way. But here's the thing. What you can see with your eyes is just a tiny fraction of what's actually out there. Most of the universe is invisible to us, and some of the most incredible structures in our galaxy are things we'll never see without special instruments. Today, we're going to talk about something that sounds like it belongs in a science fiction novel. Two enormous bubbles, each stretching 50,000 light-years into space, erupting from the center of our galaxy like cosmic exhaust plumes. These aren't made of soap and water. They're filled with superheated gas and high-energy particles, and they're so massive that if you could see them from Earth, they'd cover more than half the sky. These are called the eROSITA bubbles, named after the telescope that gave us our best look at them so far. And they're teaching us that the quiet, peaceful center of our galaxy has a violent past that we're only beginning to understand. Before we dive into this cosmic mystery, I'd love to hear from you. What's your favorite topic in space? Are you fascinated by black holes, captivated by distant galaxies, or curious about the search for life beyond Earth? Drop a comment below and let me know. And if you enjoy learning about the universe's hidden wonders, consider subscribing to the channel. It really helps us keep exploring these incredible topics together. Let's start with a simple question. How do you find something you can't see? Think about it like this. Imagine you're in a completely dark room. You can't see anything. But if you have a thermal camera, suddenly the room comes alive. You'd see warm spots where people are standing, cold spots near windows, heat rising from electronics. The room hasn't changed. You've just changed what you're looking at. That's essentially what astronomers do when they look at the universe in different types of light. Our eyes can only see visible light, that narrow band of colors from red to violet. But light comes in many forms. Radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays. Each type of light shows us something different about the universe. The bubbles are visible in X-ray light. This is high-energy light, the kind produced by extremely hot or violent processes. When doctors use it to see your bones, they're using the fact that it passes through soft tissue but gets blocked by dense bone. In space, this type of radiation tells us where things are hot, energetic, and active. Now, Earth's atmosphere blocks most of this radiation from space, which is actually good for us because it's not great for living things. But it means we need to put our telescopes in space to see what's happening out there. That's where the telescope called eROSITA comes in. It stands for Extended Roentgen Survey with an Imaging Telescope Array. Roentgen was the scientist who discovered this form of radiation, so the name is a tribute to him. This telescope was launched in 2019 aboard a Russian-German space observatory called Spectrum Roentgen Gamma. Its job was simple in concept, but incredibly ambitious in practice. Map the entire sky in this wavelength in unprecedented detail. Think of it like Google Maps, but for invisible light in space. Before this telescope, we had images of the sky in this wavelength, but they were like having a map with only major highways marked. This new survey gave us the side streets, the alleyways, the little details we'd been missing. And when the team started processing the data from their first complete scan of the sky, they found something nobody expected. Two gigantic structures, perfectly symmetrical, extending above and below the plane of the Milky Way like wings on either side of the galactic center. But here's where it gets interesting. These structures weren't completely new. Astronomers had seen hints of them before with a different telescope called Fermy. Those were called the Fermi bubbles, discovered in 2010. They showed up in gamma-ray light, which is even higher energy than X-rays. But these newly revealed structures are bigger, much bigger. They extend about 40% further out than the Fermi bubbles. Imagine finding a building you thought was 10 stories tall, only to discover it actually has 14 floors hidden in fog. That's what this discovery was like. The Fermi bubbles were impressive enough. The X-ray observations showed us the structure was even more enormous than we'd realized. These structures are related, probably part of the same phenomenon, just showing up differently in different types of light. The Fermi bubbles are like the hot core, the most energetic part. The outer bubbles are the larger envelope, filled with slightly cooler but still incredibly hot gas. When the discovery was announced in December 2020, it sent ripples through the astronomy community. Scientists had models and theories about what might be happening at the galactic center, but seeing these structures in such clear detail was like having a hypothesis confirmed and blown apart at the same time. The bubbles are sharp. That's one detail that surprised everyone. In space, things tend to blur and diffuse over time. Hot gas mixes with cooler gas. Structures fade. But the edges of these bubbles are surprisingly well defined, like someone drew them with a compass. That sharpness tells us something important. It means whatever created these bubbles did so relatively recently in cosmic terms, and probably did it fast. Let's talk about how big these things actually are, because numbers in astronomy get so large they stop meaning anything without context. Each bubble extends roughly 50,000 light-years from the galactic center. A light-year is the distance light travels in 1 year, moving at about 300,000 kilometers per second. That's about 9.5 trillion kilometers per light-year. So we're talking about structures that are 470,000 trillion kilometers from top to bottom. That number is useless to our brains. Let's make it more concrete. The Milky Way itself is about 100,000 light-years across. These bubbles extend halfway across the entire galaxy in the vertical direction. If the Milky Way were a dinner plate, these bubbles would be 2 balloons, each as wide as the plate, rising above and below it. These structures are so large that light, the fastest thing in the universe, takes tens of thousands of years just to cross them. And from our perspective on Earth, if we could see X-rays with our eyes, these bubbles would dominate the sky. The Milky Way already stretches across our night sky as that band of light we see in dark places. The structures would extend perpendicular to that band, covering an area bigger than the Big Dipper, bigger than Orion, bigger than any constellation you've ever seen. Now think about what it took to create something this large. These aren't static structures, they're expanding bubbles of hot gas, blown outward by some tremendous release of energy at the galactic center. The gas inside these bubbles is heated to millions of degrees. That's hundreds of times hotter than the surface of the Sunday. To inflate these bubbles to their current size required an amount of energy that makes our sun look like a birthday candle. We're talking about something on the order of 10 to the 56th power ergs of energy. If that number means nothing to you, don't worry. It means almost nothing to most people. Just know that it's enough energy to power the sun's entire output for millions of years. And all that energy got released in a relatively short period of time. We think the bubbles are somewhere between a few million to maybe 20 million years old. That sounds like a long time, and for human history it is. But the Milky Way is over 13 billion years old. These bubbles formed in the last 0.2% of our galaxy's lifetime. In galactic terms, they formed yesterday. The symmetry is striking. The northern bubble and southern bubble are nearly identical mirror images. They rise and fall from the galactic center like a perfectly balanced fountain. This symmetry tells us that whatever created them came from the center and expelled material equally in both directions. It wasn't some random explosion or collision. It was something more organized, more directed. Scientists measure these bubbles in multiple ways. The X-ray emission from the telescope comes from hot gas, about 3 to 6 million degrees Celsius. That gas is thin by Earth standards, thinner than the best vacuum we can create in a laboratory, but there's so much of it spread across such an enormous volume that we can detect it from across the galaxy. Inside that hot X-ray emitting gas, there's also higher energy emission that shows up in gamma rays, which the Fermi telescope detected. There's also radio emission from the same regions. Each type of light tells us something about the different components and processes happening in these structures. The total mass of gas in the bubbles is substantial. Estimates suggest millions of times the mass of our Sun, all heated and expelled from the galactic center. To put that in perspective, it's like the galactic center burped out several star clusters worth of material and blew it into these enormous cavities. To understand where these bubbles came from, we need to talk about what's at the center of our galaxy. 26,000 light-years from Earth, in the direction of the constellation Sagittarius, lies the heart of the Milky Way. You can't see it with your eyes. Too much dust and gas blocks the view. But with radio telescopes and infrared instruments that can peer through the dust, we've mapped it in incredible detail. The galactic center is crowded. Stars are packed much more densely there than in our neighborhood. If we lived near the galactic center, our night sky would be ablaze with thousands of bright stars, packed so closely together you could barely see the darkness between them. And right at the very center, there's something extraordinary, a supermassive black hole. We call it Sagittarius A. It has a mass of about 4 million times the mass of our Sun, all compressed into a region smaller than the orbit of Mercury. It's not the biggest supermassive black hole we know about. Not even close. But it's ours, and it's the one we've studied in more detail than any other. What makes black holes special is that their gravity is so strong near the event horizon, the point of no return, that even light can't escape. That's where the name comes from. But at a distance, they're just very massive objects. Despite its enormous mass, it is actually pretty quiet right now. It's not eating much. There's not a lot of gas and dust falling into it at the moment, so it's not producing much energy. We can detect it by watching stars orbit around it, moving at incredible speeds in response to its gravity. But as supermassive black holes go, it's relatively calm. That hasn't always been the case, and that's where our story gets interesting. See, supermassive black holes are hungry when they're young. In the early universe, and during periods when lots of material falls toward them, they become some of the brightest objects in the universe. As gas spirals inward toward the black hole, it forms an accretion disk, a spinning disk of material getting compressed and heated by friction and magnetic fields. The inner part of that disk can reach millions of degrees. It glows in optical light, in ultraviolet, in X-rays. But not all the material that falls toward a black hole makes it in. Some gets redirected. Magnetic fields threading through the accretion disk can channel material along the black hole's rotation axis, flinging it outward in two opposite directions as jets. These jets can travel at nearly the speed of light, carrying enormous amounts of energy and momentum out into space. When a supermassive black hole is actively feeding, producing jets, we call it an active galactic nucleus, or AGN. They're some of the most powerful phenomena in the universe. A single active galactic nucleus can outshine its entire host galaxy of hundreds of billions of stars. The jets can extend for millions of light years, plowing through intergalactic space like cosmic blowtorches. Right now, it is not an active galactic nucleus. It's sleeping, but all the evidence suggests it wasn't always asleep. This is where the bubbles come in. Most scientists think the bubbles were created during a period when the black hole woke up and went through an active phase. Something triggered it. Maybe a large cloud of gas wandered too close. Maybe a star got tidally disrupted and torn apart, its remains falling into the black hole. We don't know exactly what the trigger was, but something fed the beast. When the black hole turned on, It would have produced jets, powerful outflows of material and energy shooting outward perpendicular to the galactic plane. Those jets would have plowed into the surrounding interstellar medium, the gas and dust between the stars, and created a shock wave. Like a snowplow pushing snow into piles on either side of a road, the jets pushed material outward, creating the expanding bubbles we see today. The energy from the black hole's activity heated the gas to millions of degrees. The jets and outflows evacuated regions of space, creating the cavities. And over time, millions of years, those cavities expanded and cooled slightly, but they're still hot enough and still contain enough high-energy particles to glow brightly in X-rays and gamma rays. This is the leading theory. It's not the only one, and we'll talk about alternatives, but it's the explanation that fits most of the evidence. The structures are the smoking gun, the evidence that our galaxy's central black hole had a violent active period within the last few million years. Before we dive into the competing theories about what created these bubbles, let's talk about the people who discovered them and how international collaboration made this possible. The X-ray telescope is a product of the Max Planck Institute for Extraterrestrial Physics in Germany. But like most major astronomical discoveries today, this wasn't the work of one person or even one country. It was a collaborative effort involving hundreds of scientists from dozens of institutions across the globe. The principal investigator for the mission, the person leading the mission, is Andrea Maloney. But the team analyzing the data and making sense of what they were seeing included experts in xrayastronomy, galactic structure, plasma physics, black hole behavior, and computational modeling. Each person brought their own expertise to understanding what these structures meant. When the first complete sky survey data came in, the team had to process enormous amounts of information. We're talking about billions of X-ray photons detected over 6 months of continuous scanning. Each photon had to be catalogued, its energy measured, its direction traced back to a point in the sky. This required sophisticated software and powerful computers to handle. The initial processing revealed thousands of X-ray sources. Most were expected things like distant active galaxies, clusters of galaxies, and X-ray binary stars in our own galaxy. The team had to carefully subtract all these known sources to see the diffuse emission from structures like these bubbles. It's like trying to see the faint glow of city lights from space, while the sun is in your field of view. You need to remove the bright sources to see the subtle underlying structures. The analysis took months of careful work, checking and rechecking to make sure the signal was real and not some artifact of the data processing. When the team first saw the bubbles clearly in their processed maps, there was excitement, but also caution. In science, you don't announce a discovery until you're absolutely certain it's real. Could it be a processing error? Could it be some foreground emission from our local neighborhood of the galaxy that just happened to look like bubbles? Could it be contamination from some other source? They ran test after test, comparing different parts of the data using different processing methods, looking at the structures from every angle they could think of, and each test confirmed what they were seeing. The bubbles were real, they were enormous, and they were unlike anything seen before at this scale in our galaxy. The announcement in December 2020 came with a detailed scientific paper describing the discovery, the data analysis, and the initial interpretation. But that paper was just the beginning. Since then, dozens of follow-up papers have been published by teams around the world, each examining different aspects of the bubbles, testing different theories, comparing them to similar structures in other galaxies. This is how modern astronomy works. It's not lone geniuses working in isolation. It's teams of specialists collaborating across borders, sharing data, challenging each other's interpretations, and collectively advancing our understanding. This discovery is a perfect example of what we can achieve when we work together. The German-Russian collaboration that launched Spectrum Roentgen Gamma, the spacecraft carrying the telescope, is another example of international cooperation. Despite political tensions that sometimes exist between nations, scientists continue to work together, united by curiosity and the desire to understand the universe. The structures are as much a triumph of human cooperation as they are of human ingenuity. Science is about evidence and interpretation. When we see something like these structures, there's rarely just one possible explanation. Let's explore the alternatives. The main competing theory is that the bubbles were created not by the supermassive black hole, but by an intense period of star formation at the galactic center. Here's how that would work. Stars don't live forever. Massive stars, stars much bigger than our Sun, live fast and die young. They burn through their nuclear fuel in just a few million years instead of the billions of years smaller stars take. And when massive stars die, they die spectacularly. They explode as supernovae. One supernova releases more energy than the Sun will produce in its entire 10 billion year lifetime, all in a few seconds. It's violent, sudden, and incredibly powerful. The explosion sends a shockwave racing outward at thousands of kilometers per second, sweeping up surrounding gas and heating it to millions of degrees. Now, imagine not one supernova, but thousands, maybe tens of thousands, all concentrated in the galactic center, all going off over a period of a few million years. That's what happens during a starburst, a period of intense star formation. In a starburst, conditions conspire to make stars form much faster than normal. Maybe two galaxies collide and their gas clouds smash together, compressing them and triggering collapse. Maybe a density wave passes through a galaxy, compressing gas as it goes. Whatever the trigger, suddenly you have lots of massive stars forming close together. And when all those massive stars die as supernovae over a relatively short time, the combined energy can be staggering. The shock waves from multiple supernovae can merge, creating a superbubble. The collective force of thousands of stellar explosions can drive powerful winds out of the galaxy. This is called a galactic superwind, and we've seen them in other galaxies. They look remarkably similar to what we see with the structures. Hot gas, X-ray emission, expanding cavities, extending perpendicular to the galactic plane. So could these bubbles have been created by a starburst rather than by Sagittarius A? It's possible. The galactic center does have intense star formation. There are young, massive stars there right now. And we know there have been periods of higher star formation in the past. The challenge is timing and energy. To create bubbles this large from supernovae, you need a lot of supernovae concentrated in a short time. The numbers are plausible, but tight. You need millions of solar masses worth of stars to form, live, and die, all releasing their energy in a coordinated way to blow the bubbles outward. Proponents of the black hole theory point out that a single active galactic nucleus episode can more easily deliver the required energy in a short burst. A million-year feeding frenzy for it could do the job. You don't need to coordinate thousands of separate supernova events. Proponents of the starburst theory point out that we see evidence of ongoing star formation at the galactic center and that starbursts are common in galaxy centers. Why invoke the black hole if stars can do the job? The truth might be somewhere in between. It's possible both processes contributed. Maybe a starburst initiated the bubbles, and then the black hole woke up and added its energy to the mix. Maybe the starburst was actually triggered by an earlier burst of activity from the black hole. Astronomy is rarely simple, and complex structures often have complex origins. There's also a third, more exotic possibility that some researchers have explored. What if the bubbles are much older than we think, and we're just seeing the remnants of something that happened hundreds of millions of years ago? This idea is harder to support, because of the sharp edges of the bubbles. In space, structures blur and fade over time. The fact that the bubbles have such well-defined boundaries suggests they're relatively young and actively maintained by some ongoing energy input, or that they formed recently enough that they haven't had time to dissipate. But perhaps there's some mechanism we don't understand that keeps the boundaries sharp. Perhaps the magnetic fields in the region create barriers that prevent mixing. It's speculative, but science requires us to consider all possibilities until the evidence rules them out. Right now, the leading theory remains the supermassive black hole activity. It's the simplest explanation that fits the energy requirements, the symmetry, the sharp boundaries, and the timing. But the starburst theory is still in play, and ongoing observations will help us figure out which is correct. How do we know how old the bubbles are? You can't exactly count rings like a tree or use carbon dating on hot gas floating in space, but astronomers have clever ways of reading the cosmic clock. First, there's the size. We can measure how big the bubbles are. If we know how fast they're expanding, we can work backward to figure out when they started. It's like watching a balloon inflate. If you know its current size and how fast it's growing, you can calculate when someone started blowing into it. The challenge is measuring the expansion speed. The bubbles are enormous, and we're watching from one specific point in space. We can use something called the Doppler shift to measure motion. When something moves toward you, the light it emits gets compressed to shorter wavelengths, shifted toward the blue end of the spectrum. When something moves away, the light gets stretched to longer wavelengths, shifted toward red. By looking at different parts of the bubble and measuring how their light is shifted, we can map their motion. The edges appear to be expanding at hundreds of kilometers per second. That's fast by Earth standards, faster than any rocket we've built, but actually pretty typical for structures driven by galactic scale events. Working backward from the current size and expansion speed, we get ages in the range of a few million to perhaps 20 million years. There's uncertainty because we don't know if the expansion rate has been constant. The bubbles might have expanded faster at first and slowed down over time as they ran into more resistance. Or maybe the expansion was driven by multiple bursts of energy, not just one. Another clock comes from the cooling time of the gas. The X-rays we see are emitted by hot gas. Hot things cool down over time. In space, hot gas cools by radiating its energy away as light. We can calculate how long it takes for gas at millions of degrees to cool to a temperature where it would no longer emit X-rays. Based on the temperature and density of the gas in the bubbles, scientists calculate cooling times of several million years. That gives us a maximum age. If the bubbles were much older, the gas would have cooled below the point where we detect it in X-rays. There's also evidence from the galactic center itself. We can look for signs of recent activity around it. While it's quiet now, we can look for echoes of past activity. One fascinating line of evidence comes from something called light echoes. When the black hole was active, it would have emitted intense light in all directions. Most of that light has long since passed us by. But some of it hit clouds of gas at various distances from the center. Those clouds absorbed the energy and re-emitted it, creating an echo that's still traveling outward. By looking at the spectra of certain gas clouds near the galactic center, astronomers have found evidence that they were hit by intense radiation in the relatively recent past. The timing matches up with the age estimate for the bubbles. It's like finding someone's footprints in concrete that hasn't fully hardened yet. The footprints prove they were there recently. There's also chemical evidence. The gas in the bubbles isn't the same composition as typical interstellar gas. It's enriched in certain elements that come from stars, elements like iron, silicon, and oxygen in specific ratios. This enrichment tells us something about the source. If the bubbles were purely from the black hole eating interstellar gas, we'd expect different abundances. The chemical signature suggests that material from stars, either from stellar winds or supernovae, contributed to the mix. This doesn't rule out the black hole theory. Stars exist at the galactic center too, and a black hole's activity would sweep up nearby stellar material and incorporate it into the outflow. But it does tell us the story is complicated. We can also look at the morphology, the shape and structure. The bubbles aren't perfectly smooth. There are features within them, filaments, and brighter regions that suggest substructure. These features can tell us about the history of the expansion. Did it happen in one burst or multiple bursts? Was the energy released uniformly or in jets that wobbled over time? High-resolution observations show that the inner regions, the Fermi bubbles, have more structure than the outer envelope. This makes sense if the Fermi bubbles trace the most recent and most energetic activity, while the bubbles are the older, cooler, outer layer. Think of it like the layers of an onion. The outer layers formed first and have had more time to cool and expand. The inner layers are younger, still hotter and more energetic. By studying both together, we can reconstruct the timeline of events. All these clocks, size, expansion speed, cooling time, light echoes, and chemical signatures point to a consistent story. Something happened at the galactic center roughly 5 to 10 million years ago. It released an enormous amount of energy in a relatively short time. That energy created the bubbles we see today. And while we're still working out the exact details of what happened, we're confident about the basic timeline. Inside these structures, there's an invisible particle accelerator at work. Let's talk about cosmic rays and the extreme physics happening in these structures. Cosmic rays are one of the most misnamed things in astronomy. They're not rays at all. They're particles, mostly protons, the nuclei of hydrogen atoms traveling through space at nearly the speed of light. Some cosmic rays have energies so high that a single particle carries as much kinetic energy as a baseball thrown by a professional pitcher. That's mind-boggling when you remember that a proton is about a billion times lighter than a baseball. Where do cosmic rays come from? That's one of the big unsolved questions in astrophysics. We know some come from supernova explosions. When a star explodes, the shockwave racing outward can accelerate particles to tremendous speeds. We know some come from active galactic nuclei, accelerated in the jets and outflows from supermassive black holes. But the exact mechanisms are still being worked out. The structures are a laboratory for studying cosmic ray acceleration. The gamma-ray emission detected by the Fermi telescope tells us there are high-energy particles in the bubbles. When cosmic ray protons collide with other protons in the gas, they can create particles called pions. Those pions quickly decay, producing gamma rays. This is one way the bubbles produce the gamma-ray glow we observe. There's also another process. High-energy electrons in the bubbles can collide with low-energy photons, light particles, and boost them to gamma-ray energies. This is called inverse Compton scattering. It's like a game of cosmic billiards. The electron is the cue ball, the photon is the target ball, and the collision sends the photon flying off with much more energy than it started with. Both processes are probably happening in these bubbles. Teasing apart how much of the gamma-ray emission comes from protons versus electrons is a challenge that researchers are still working on. The answer matters because it tells us about the composition and origin of the cosmic rays in the bubbles. The edges of the bubbles are particularly interesting for particle acceleration. When the expanding bubble runs into the surrounding interstellar medium, it creates a shock wave. Think of it like a bow wave in front of a boat. The boat pushes water aside, creating a wave that travels ahead of it. In space, the expanding bubble pushes gas aside, creating a shock. Shocks are nature's particle accelerators. Here's how it works. When a particle crosses the shock, it gains energy. Magnetic fields on either side of the shock can bounce the particle back and forth across the shock multiple times. Each time it crosses, it gains more energy. This process, called diffusive shock acceleration, is one of the main ways cosmic rays are created throughout the universe. They have shock fronts at their leading edges, where they're still expanding into the surrounding gas. These shocks have been working for millions of years, accelerating particles to higher and higher energies. Some of those particles escape the bubbles and travel through the galaxy. They might eventually reach Earth, where we detect them as cosmic rays arriving from space. In fact, there's an interesting puzzle related to this. For decades, astronomers have known that there's an excess of cosmic ray positrons, the antimatter counterparts of electrons, arriving at Earth compared to what we'd expect. The source of these positrons has been a mystery. Some exotic theories suggested they might come from dark matter particles annihilating each other. But a more mundane explanation might be that they come from processes in structures like these bubbles. When high-energy protons collide and create pions, some of those pions decay into positrons. If these bubbles have been producing cosmic rays for millions of years, they could be a significant source of the positrons we detect. This is still being investigated, but it shows how studying the bubbles connects to broader questions in astrophysics. There's also the question of the maximum energy cosmic rays can reach in the bubbles. The acceleration process isn't unlimited. Eventually, particles either escape the acceleration region, or they lose energy through radiation, or the shock itself isn't strong enough to accelerate them further. Understanding these limits helps us understand not just these bubbles, but cosmic ray acceleration throughout the universe. The magnetic fields in the bubbles play a crucial role in all of this. Without magnetic fields, charged particles would just fly away in straight lines. The magnetic fields trap particles, making them spiral around field lines and keeping them in the acceleration region long enough to gain energy. The strength and structure of these fields determine how efficiently particles can be accelerated and how long they stay in the bubbles. Researchers use computer simulations to model particle acceleration in the bubbles. These simulations solve equations describing how particles move in magnetic fields, how they interact with shocks, how they radiate energy. By comparing the simulation results to the gamma-ray and X-ray observations, scientists can test their understanding of the physics and refine their models. One fascinating aspect is that the cosmic rays produced in these bubbles might affect the galaxy beyond the bubbles themselves. As these high-energy particles escape and travel through the Milky Way, they can influence the interstellar medium. They contribute pressure that can affect gas dynamics. They can ionize gas, changing its chemistry. They can even influence star formation in subtle ways. So these bubbles aren't just isolated structures. They're sources of cosmic rays that have been seeding the galaxy with high-energy particles for millions of years. This connects the bubbles to the larger story of how our galaxy works, how energy and matter flow through it, and how different processes interact to shape its evolution. Let's talk more about the relationship between the bubbles and the Fermi bubbles, because understanding how they fit together is key to understanding the whole structure. The Fermi bubbles were discovered in 2010, revealing two lobes of gamma-ray emission extending about 25,000 light-years in each direction from the galactic center. They were surprising because, like these structures, they showed our galaxy's center had experienced something energetic in the recent past. The gamma-ray emission told scientists that there were cosmic rays in those regions, particles accelerated to nearly the speed of light. When those cosmic rays collide with lower energy photons or interact with gas, they can produce gamma rays through various processes. The discovery of the Fermi bubbles was exciting, but they were hard to study in detail because gamma rays are difficult to focus. Gamma ray telescopes don't work like optical telescopes. They're more like particle detectors, counting individual gamma-ray photons and trying to figure out where they came from. This means the images are relatively fuzzy. When the telescope scanned the sky and revealed the X-ray bubbles, the connection was immediately obvious. These bubbles and Fermi bubbles are aligned along the same axis, perpendicular to the galactic plane. They have similar shapes, both roughly elliptical, and the X-ray bubbles extend further out, like a larger shell surrounding the Fermi bubbles. The relationship makes sense when you think about the physics. An energetic event at the galactic center would create an outflow. Close to the center, where the energy is most intense, particles get accelerated to the highest energies, producing gamma rays. That's the Fermi bubbles. Further out, the outflow expands and cools, but the gas is still hot enough to emit X-rays. That's these bubbles. It's like the difference between the flame of a blowtorch and the hot air around it. The flame itself is the hottest part, glowing bright. The air heated by the flame is cooler, but still hot enough to feel. The Fermi bubbles are the flame. The structures are the hot air. There's also radio emission detected from the same regions by radio telescopes. Radio waves can be produced by relativistic electrons moving at nearly the speed of light, spiraling around magnetic fields. This process is called synchrotron radiation, and it's common in astrophysical jets and outflows. So we have gamma rays from the Fermi bubbles, X-rays from these bubbles, and radio emission from the same structures. Each type of light is telling us about different particles and processes, but they're all part of the same phenomenon. It's like studying an elephant. One person touches the trunk, another touches the ear, another the leg. Each person describes something different, but they're all describing parts of the same animal. Scientists have used this multi-wavelength approach to build models of what's happening. The leading models suggest that the bubbles are filled with a mix of hot thermal gas, which emits the X-rays, and non-thermal particles, relativistic electrons and protons, which produce the gamma rays and radio emission. The thermal gas is heated by shocks, sudden compressions of gas when the outflow runs into the surrounding interstellar medium. Think of it like a sonic boom. When a jet aircraft breaks the sound barrier, it creates a shock wave in the air that produces a sudden pressure and temperature increase. The same thing happens in space when high-speed outflows run into ambient gas. The non-thermal particles are accelerated by those same shocks or by magnetic reconnection events in the turbulent plasma. Once accelerated, these particles can maintain their high energies for millions of years, continuing to produce gamma rays and radio emission long after the initial event that created them. The edges of the bubbles, particularly where they're brightest, are likely where the most efficient particle acceleration is happening. These edges are moving, still expanding, still sweeping up material and generating shocks. That's why the boundaries are so sharp. They're actively maintained by the ongoing expansion. One interesting detail is that the northern and southern bubbles aren't perfectly identical. The northern bubble is slightly brighter in some wavelengths. This asymmetry might be due to differences in the surrounding interstellar medium. Maybe the northern direction had more gas to plow through, creating more shocks and brighter emission. Or maybe our view from Earth is slightly off-axis and we're seeing a projection effect. The combined picture from Fermi, X-ray observations, and radio telescopes gives us the most complete view yet of these structures. They're not simple bubbles of hot gas. They're complex, multi-phase regions filled with gas at different temperatures, cosmic rays at different energies, and magnetic fields threading through the entire structure. The structures aren't just moving gas around, they're redistributing the chemical elements that make up everything we see in the universe. Let's explore how these structures affect the galaxy's chemistry. When the universe began in the Big Bang, only the lightest elements were created. Hydrogen and helium made up almost everything, with tiny traces of lithium. All the heavier elements, everything from carbon to iron to gold, were created later inside stars or in stellar explosions. Astronomers call all these heavier elements metals, even though a chemist would object that carbon and oxygen aren't metals. It's just terminology. Stars are cosmic factories. In their cores, nuclear fusion combines lighter elements into heavier ones. Small stars, like our Sun, fuse hydrogen into helium. Larger stars go further, creating carbon, nitrogen, oxygen, and beyond. The most massive stars create elements all the way up to iron in their cores. And when these massive stars explode as supernovae, the incredible energies involved create even heavier elements like gold, platinum, and uranium. All these newly created elements get ejected into space when stars die, some gently through stellar winds as stars age, some violently in supernova explosions. This material mixes into the interstellar medium, enriching it with metals. The next generation of stars that forms from this enriched gas will have those metals from the start. The galactic center is a special place chemically. It's been forming stars for billions of years, longer and more intensely than our neighborhood. That means there have been more generations of stars living and dying, more supernovae enriching the gas, higher concentrations of metals in the interstellar medium there. When the bubbles formed, they didn't just push out ordinary hydrogen and helium. They carried with them gas, enriched with metals from billions of years of stellar evolution at the galactic center. This metal-enriched gas is now spread throughout the bubbles, 50,000 light-years from where it originated. Spectroscopy, the study of light split into its component colors, lets us measure the chemical composition of the gas in the bubbles. Different elements emit light at specific wavelengths when heated. By looking at which wavelengths are present and how bright they are, we can determine what elements are in the gas and in what proportions. Studies of these bubbles have found that the gas is indeed enriched in metals compared to typical interstellar gas at the same distance from the galactic center. There's more iron, more silicon, more oxygen than you'd expect. This is a fingerprint of the galactic center, carried outward by the expanding bubbles. The iron is particularly interesting. Most of the iron in the universe comes from supernova explosions. There are two main types of supernovae, and they produce iron in different amounts and with different isotopic ratios. By studying the iron in the bubbles, astronomers can learn about the types of supernovae that occurred at the galactic center before the bubbles formed. There's also neon, magnesium, and sulfur, elements that come from different stages of stellar evolution and from different types of stars. The full chemical inventory of the bubbles is like a fossil record, preserving information about the history of star formation and stellar death at the galactic center. This chemical enrichment has implications beyond just understanding the bubbles themselves. The metal-enriched gas in the bubbles will eventually mix with the surrounding interstellar medium and the circumgalactic medium. Some might even escape the galaxy entirely, joining the intergalactic medium. Wherever it goes, it carries the chemical signature of the galactic center. Future generations of stars that form from this enriched gas will have slightly different compositions than they would have otherwise. They'll have more metals, which affects their evolution, their opacity to light, the types of planets that can form around them. In a very real sense, the bubbles are influencing the future chemical evolution of our galaxy. There's also a connection to planet formation. Rocky planets like Earth are made primarily of metals in the astronomical sense. Silicon, iron, magnesium, oxygen combined into minerals and rocks. The more metals in a star-forming region, the more raw material there is to build rocky planets. By spreading metal-enriched gas through a large volume of the galaxy, these bubbles might be seeding future planetary systems. One fascinating detail is that the chemical enrichment isn't uniform throughout the bubbles. Some regions show higher metal content than others. This suggests that the bubbles didn't form from a completely well-mixed reservoir of gas. There might have been different components contributing at different times, or there might be ongoing mixing processes that haven't fully homogenized the gas yet. Researchers are also looking for elements that can only be created in specific environments. For example, certain isotopes of aluminum and iron are created in supernova explosions and decay relatively quickly on cosmic timescales. Finding these isotopes in the bubbles would tell us about the timing of supernova events near the galactic center and how soon after those explosions the bubbles formed. There's even a search for the signature of nuclear reactions that might occur in the vicinity of an active black hole. In the intense radiation field near an actively feeding supermassive black hole, nuclear reactions can happen in ways that don't occur anywhere else. These reactions can create unusual isotopic ratios or rare elements. Finding such signatures would be smoking gun evidence that the black hole's activity directly contributed to creating the bubbles. The study of chemical enrichment in the bubbles connects to a broader field called galactic chemical evolution, which tracks how the composition of galaxies changes over cosmic time. By understanding how elements are created, how they're distributed, and how they're mixed, we can build a complete picture of how galaxies like the Milky Way evolved from simple clouds of hydrogen and helium into the complex, metal-rich systems we see today. Though these bubbles don't exist in isolation, they're part of a larger ecosystem at the galactic center, interacting with other structures and influencing their surroundings. Our galaxy isn't empty space with stars floating in it. Between the stars, there's the interstellar medium, gas and dust, filling the space between. Near the galactic center, this medium is denser and more complex than in our neighborhood. There are giant molecular clouds, regions where gas is cold enough and dense enough to form molecules. There are ionized regions around hot young stars. There are supernova remnants, expanding shells from dead stars. And now, we know there are these enormous bubbles. When the bubbles were created, they didn't just inflate into empty space. They pushed against the existing interstellar medium. This interaction shaped both the bubbles and the surrounding gas. Think of it like blowing a bubble underwater. The bubble rises, but as it does, it displaces water. The water has to move out of the way. The same thing happens in space. As the bubbles expanded, they pushed the surrounding gas aside, compressing it at the boundaries. This compression can actually trigger star formation. When gas gets compressed, it can become dense enough to collapse under its own gravity and form stars. So the bubbles might have seeded new generations of stars along their edges. We see this in other galaxies where galactic-scale outflows interact with the interstellar medium. Rings or shells of young stars form where the outflow compressed the gas. There's also the question of where all this gas goes. The bubbles are expanding outward, carrying material with them. Some of that material will eventually escape the galaxy entirely, becoming part of the circumgalactic medium, the halo of hot gas that surrounds the Milky Way. This process of removing gas from a galaxy is called feedback, and it's crucial to understanding how galaxies evolve. Without feedback, galaxies would turn all their gas into stars very quickly. But feedback, whether from supernova explosions, stellar winds, or activity from the central black hole, drives gas out of the galaxy, regulating star formation. The structures are a dramatic example of this feedback. They've ejected millions of solar masses of gas from the galactic center. That gas is no longer available to form stars. In that sense, the bubbles have shaped the evolution of our galaxy, determining where and when stars could form. There's also interaction with the galaxy's magnetic field. The Milky Way has a large-scale magnetic field threading through it. this field isn't uniform. It has structure, with field lines that spiral along the disk of the galaxy. When the bubbles expanded, they stretched and compressed these magnetic field lines. Magnetic fields can act like rubber bands. Stretch them too much and they snap, reconnecting in new configurations and releasing energy. This process, called magnetic reconnection, can accelerate particles to high energies. It might be one of the mechanisms producing the cosmic rays we detect in the Fermi bubbles. The magnetic fields also help maintain the structure of the bubbles. Charged particles, like the hot ionized gas in the bubbles, can't easily cross magnetic field lines. They're confined, channeled along the fields. This confinement can prevent mixing and help keep the boundaries of the bubbles sharp. There's a structure called the galactic bar that's also relevant. The Milky Way isn't a perfect spiral. The inner part of our galaxy has a bar shape, a rectangular structure of stars and gas stretching across the center. This bar influences gas flows, funneling material toward or away from the very center, depending on its orbit. Some researchers think the bar might have played a role in triggering the activity that created the bubbles. Perhaps the bar channeled gas inward toward it, feeding it and triggering an active phase. Or perhaps the bar's gravitational influence helped direct the outflow once it started, shaping the symmetry we see. We also need to think about smaller scale structures within the bubbles. Observations have revealed filaments, long, thin structures of brighter emission threading through the bubbles. These filaments are likely magnetic field lines made visible by particles spiraling along them, or they could be denser regions of gas that emit more strongly. There are also cavities within cavities, suggesting multiple episodes of energy injection. Maybe it turned on and off several times, each burst creating a new shell. Or maybe there were multiple sources of energy, the black hole plus several supernovae, all contributing at different times. Understanding these details requires careful comparison of observations at different wavelengths and computer simulations that model the physics of expanding bubbles in a realistic galactic environment. It's painstaking work, but each new detail we uncover helps us understand not just these structures, but how similar structures form in other galaxies. Here's a question that might not immediately come to mind when looking at giant bubbles of superheated gas, but it's worth asking. What do they tell us about where life can exist in our galaxy? The search for life beyond Earth is one of the most compelling questions in science. We know life exists on Earth. We don't know if it exists anywhere else. But we can ask where the conditions might be right for life to emerge and survive. That's led to the concept of the galactic habitable zone. Just as there's a habitable zone around a star, a region where planets can have liquid water on their surface, there's arguably a habitable zone in the galaxy. Too close to the galactic center, and conditions might be too harsh. Too far out, and there might not be enough heavy elements to form rocky planets. These bubbles give us information about conditions near the galactic center. The fact that such enormous, energetic structures can be created there tells us that the inner galaxy experiences periodic violent events. A planet orbiting a star in that region would need to contend not just with a crowded stellar environment, but also with these episodic outbursts. Now, the direct effects on a planet would be small. The gas in the bubbles is incredibly thin. Even if a solar system were engulfed by one of the bubbles, it wouldn't be like being hit by a solid object. But there would be indirect effects. The cosmic rays accelerated in the bubbles could reach higher intensities in the inner galaxy. Cosmic rays can damage DNA and strip away planetary atmospheres if they're intense enough. Earth is protected from cosmic rays by our magnetic field and atmosphere. But a planet with a weaker magnetic field or thinner atmosphere might be more vulnerable. If the inner galaxy has higher background cosmic ray levels due to structures like these bubbles, that might make it harder for life to survive there. On the other hand, Cosmic rays aren't purely destructive. In moderate amounts, they can drive interesting chemistry in planetary atmospheres. Some theories suggest that cosmic rays might have played a role in the origin of life on Earth by helping to create complex organic molecules. So the relationship between cosmic rays and life is complicated. There's also the question of how these bubbles affect star formation in different parts of the galaxy. By removing gas from the galactic center, the bubbles reduce the fuel available for forming new stars. That means fewer new planetary systems forming in that region. But along the edges of the bubbles, where gas is compressed, star formation might be triggered. Those stars would form from gas enriched with metals from the galactic center, giving any planets that form around them a different composition than planets forming elsewhere. The distribution of life in the galaxy might not be uniform. If the inner regions are periodically subjected to violent events like those that created these bubbles, perhaps life is more common in the outer regions where conditions are calmer. Our location in the Milky Way, about halfway out, might not be a coincidence. Perhaps it's the sweet spot where conditions are stable enough for complex life to evolve over billions of years. This connects to something called the rare Earth hypothesis, which suggests that while simple life might be common in the universe, complex life like animals and plants might be rare because it requires a very specific set of conditions. The structures are a reminder that galaxies are dynamic, sometimes violent places. Regions that seem stable might not have been stable throughout cosmic history. There's also an interesting connection to astrobiology's concept of biosignatures. If life exists on planets elsewhere in the galaxy, we might detect it by looking for signs of biological activity in their atmospheres. Gases like oxygen, methane, or more exotic molecules produced by life. But cosmic rays from structures like these bubbles could alter atmospheric chemistry in ways that might mimic or mask biosignatures. Understanding the cosmic ray environment in different parts of the galaxy helps us interpret what we might see when we start studying exoplanet atmospheres in detail. Looking beyond our own galaxy, these bubbles might also tell us something about the habitability of other galaxies. Small galaxies with less active black holes might not have structures like these. They might be quieter, safer places for life. Giant elliptical galaxies with much more massive black holes might have much more violent feedback events, making their inner regions inhospitable. The Milky Way might represent a middle ground. We have a supermassive black hole, but it's relatively modest in mass. It has periodic bursts of activity that create structures like these bubbles, but these aren't continuously active like in some other galaxies. This intermittent activity might actually be beneficial, regulating star formation and distributing elements without being so violent that it sterilizes large regions of the galaxy. Of course, we're speculating here. We don't know that life exists anywhere besides Earth. We don't know what conditions are truly necessary for life to emerge. But thinking about how structures like these bubbles affect galactic environments helps us refine our thinking about where to look for life and what conditions might favor it. As we build more powerful telescopes and start studying planets around other stars in detail, the lessons we learn from studying our own galaxy will be crucial. The structures are part of the environmental context for life in the Milky Way. Understanding them helps us understand our cosmic neighborhood and what makes it suitable or unsuitable for life to flourish. The structures are giving us new insights into how supermassive black holes behave, and that has implications far beyond our own galaxy. One of the biggest questions in astrophysics is how supermassive black holes grow. We know they exist. We've detected them in most large galaxies we've looked at. Some are billions of times the mass of the Sun. But how did they get so big? Black holes grow by eating. They accrete material, whether it's gas, dust, or unlucky stars that get too close. But there's a problem. As material falls toward a black hole, it forms an accretion disk. That disk gets hot and starts radiating energy. That radiation creates pressure that pushes outward, counteracting gravity. There's a limit to how fast a black hole can grow, called the Eddington limit. Beyond this rate, the radiation pressure from the accretion disk would blow away incoming material faster than the black hole could eat it. It's self-limiting. To grow a billion solar mass black hole in the age of the universe, starting from stellar mass black holes formed from the first stars, requires growth at or near the Eddington limit for billions of years. That seems unlikely. There should be interruptions, times when material isn't available, times when feedback blows gas away. The structures are an example of that feedback in action. When the black hole was active, it didn't just grow. It expelled material. It pushed gas away from the galactic center. This temporarily stops its own growth. But here's the interesting part. By clearing out the region around it, the black hole might be setting the stage for future growth. The expelled gas might eventually cool, fall back, and feed the black hole again in millions of years. Or fresh gas might fall in from the outer galaxy, and without the clutter of nearby gas and dust, it might fall in more efficiently. This cycle of feeding, expelling, and feeding again might be how supermassive black holes grow, not in one continuous process, but in bursts separated by millions of years of quiescence. We see this pattern in other galaxies. Many large galaxies have central black holes that appear inactive, like ours. But we also see active galactic nuclei, galaxies where the central black hole is currently feeding vigorously. And we see intermediate cases, galaxies with signs of recent activity but not currently active. These bubbles tell us that our galaxy's black hole was active recently and is now quiet. We're in the quiescent phase, but the evidence of the active phase is still visible. By studying our own galaxy's history, we can understand the histories of other galaxies. There's also the question of what triggers activity. Why did Sagittarius A turn on a few million years ago? And why did it turn off? One possibility is that it's stochastic, random. Gas clouds wander through the galactic center all the time. Most of them don't get close enough to the black hole to matter. But every few million years, maybe one gets unlucky and falls in, providing a feast. Another possibility is that there are cycles driven by larger-scale processes. Maybe interactions with nearby satellite galaxies disturb the Milky Way's gas, sending waves of material inward. Maybe the galactic bar channels gas inward periodically. Maybe there's some other mechanism we haven't identified yet. Understanding these triggers is important because it helps us predict what will happen next. Will Sagittarius A turn on again? When? How often does this cycle repeat? These bubbles also tell us about the energetics of black hole activity. By measuring how much energy went into creating the bubbles, we can estimate how much material the black hole consumed during its active phase. Current estimates suggest the black hole consumed somewhere between 10,000 and 100,000 solar masses of material. That's a lot, but it's a tiny fraction of the black hole's current mass. It is 4 million solar masses. Adding another 100,000 wouldn't change it much. But in terms of the energy released, it's enormous. Only a fraction of the infalling material's mass energy gets converted to radiation and kinetic energy in the jets. Most of it falls into the black hole, but that fraction is still enough to power the bubbles we see. There's also evidence from the bubbles about the structure of the jets themselves. The symmetry of the bubbles suggests the jets were well collimated, meaning they stayed focused rather than spreading out. The sharp edges suggest the jets were powerful, punching through the interstellar medium rather than being deflected. Some models suggest the jets might have wobbled or precessed over time, like a spinning top. This would create a cone of influence rather than a narrow beam. Features within the bubbles might reflect this wobbling, creating the filaments and substructure we observe. All these details are clues about the physics of jets, which we still don't fully understand. Jets are magnetically driven. The magnetic field threading through the accretion disk gets twisted by the disk's rotation and by the black hole's spin, creating a magnetic tower that flings material outward. But the exact mechanisms of how magnetic fields launch and collimate jets are still being worked out, both theoretically and through observations like the structures. The Milky Way isn't unique. Other galaxies have similar structures, and studying them helps us understand what we're seeing at home. Let's start with our nearest large galactic neighbor, Andromeda, also known as M31. It's about 2.5 million light-years away, close enough that we can study it in great detail. Andromeda also has a supermassive black hole at its center, about 100 million solar masses, much bigger than ours. X-ray observations of Andromeda haven't revealed structures quite like these structures, but that might be because we're viewing it edge-on. Andromeda's disk is tilted relative to us. If it had bubbles extending perpendicular to its disk, we might be looking along the plane of those bubbles rather than seeing them from the side, making them harder to detect. But there are other galaxies where we do see similar structures. One famous example is NGC 3034, a nearby galaxy about 11.5 million light-years away. It's viewed almost edge-on, which is perfect for seeing structures extending above and below the galactic plane. NGC 3034 has an active galactic nucleus. Its central black hole is currently feeding, producing jets visible in radio wavelengths. But it also has enormous lobes of X-ray emission extending above and below the disk, similar to the structures. These lobes are the result of the jets interacting with the surrounding gas, creating hot bubbles of shocked gas. The NGC 3034 bubbles are smaller than ours, extending only about a few thousand light-years. But the galaxy itself is smaller than the Milky Way, so in relative terms, they're comparable. And the mechanisms creating them are likely very similar. Another example is the galaxy Centurus A, one of the brightest radio galaxies in the sky. It's about 10 to 16 million light-years away, relatively close in cosmic terms. Centurus A has an active black hole producing spectacular jets that extend for hundreds of thousands of light-years, far beyond the visible galaxy. But closer to the center, within a few thousand light-years, there are structures that look a lot like the structures. Hot X-ray emitting gas in lobes perpendicular to the disk. These lobes are younger than the giant jets, probably created by a more recent burst of activity. Studying Centurus A is like seeing a more active version of what might have happened in the Milky Way. If we could go back a few million years and watch Sagittarius A during its active phase, it might have looked similar. There are also examples from galaxies undergoing starbursts. The galaxy M82, the Cigar Galaxy, is one of the best-studied starburst galaxies. It's undergoing an intense burst of star formation, probably triggered by gravitational interactions with its neighbor M81. M82 has a galactic superwind, hot gas streaming out perpendicular to its disk, visible in X-rays, optical, and radio wavelengths. This wind is driven by supernova explosions from all the massive stars forming and dying in the galaxy's center. The structure looks remarkably similar to the structures. This is one reason some researchers favor the starburst model for the Milky Way's bubbles. We have clear examples of other galaxies where starbursts create similar structures. But we also have examples where black holes do it, like NGC 3034. Nature uses both mechanisms, and in some cases, probably uses both at once. There are even examples in much more distant and larger galaxies. Some giant elliptical galaxies have X-ray cavities in the hot gas surrounding them. These cavities are carved out by jets from their supermassive black holes. The jets push the gas aside, creating bubbles that can be hundreds of thousands or even millions of light years across. These systems are older and larger than these structures, but the physics is similar. Energy from the black hole creates cavities in the surrounding medium. The difference is scale. Elliptical galaxies are surrounded by enormous halos of hot gas, and their black holes are often much more massive and powerful than ours. By comparing the Milky Way to these other systems, we can understand where our galaxy fits in the bigger picture. We're seeing a relatively modest example of a process that happens across the universe, from small galaxies like M82 to giant ellipticals hosting billion solar mass black holes. One particularly interesting comparison is with the galaxy NGC 4258, which has one of the most powerful known galactic superwinds. Observations suggest that winds like this can completely quench star formation in a galaxy's center by removing all the gas. Over time, this transforms a star-forming galaxy into a passive one. Could the bubbles have quenched star formation in the Milky Way's center? Probably not completely, since we still see star formation there, but they might have reduced it, at least temporarily. And in the longer term, this cycle of feedback might regulate how our galaxy evolves, preventing it from turning all its gas into stars too quickly. Let's talk about how we actually study these structures, because the technology involved is pretty remarkable. The X-ray telescope, as mentioned earlier, is an X-ray instrument. But building an X-ray telescope is very different from building an optical telescope. You can't use normal mirrors because X-rays pass through most materials rather than reflecting off them. Instead, X-ray telescopes use grazing incidence mirrors. The X-rays hit the mirror at a very shallow angle, almost parallel to the surface, and bounce off like a stone skipping on water. These mirrors are nested cylinders, creating a tunnel that focuses X-rays onto a detector at the back. The telescope has 7 identical mirror modules, each with its own detector. This gives it a large field of view and good sensitivity. It spins slowly, scanning the sky in strips, building up a complete map over the course of 6 months. After 4 complete scans, scientists had the data showing the bubbles in unprecedented detail. The Fermi gamma-ray space telescope works differently. Gamma rays are so energetic they can't be focused at all. Instead, Fermi uses a technique called pair conversion. When a high-energy gamma ray hits a thin layer of material in the detector, it can convert into an electron-positron pair. The telescope tracks these particles as they move through the detector, reconstructing the direction the original gamma ray came from. It's like catching bullets by letting them hit a plate and watching the splatter. You can figure out where the bullet came from by analyzing the pattern. Fermi does this for thousands of gamma rays every day, slowly building up images of the gamma ray sky. Radio telescopes are more straightforward. They use large dishes or arrays of antennas to collect radio waves from space. Radio waves are low energy, but they have the advantage of passing through dust and clouds that block optical light. This makes them perfect for studying the galactic center, which is heavily obscured in visible light. The Murchison Wide Field Array in Australia and the Meerkat Telescope in South Africa are 2 modern radio telescopes that have contributed to mapping the structures associated with the structures. They've revealed filaments and structures within the bubbles at incredible resolution. Infrared telescopes, like NASA's Spitzer Space Telescope and the James Webb Space Telescope, can also peer through dust to see the galactic center. While they don't detect the bubbles directly, they map the stars and gas in the region, providing context for where the bubbles formed and what they're interacting with. And then there's the Event Horizon Telescope, a global network of radio dishes that achieve the remarkable feat of imaging the shadow of a black hole. They've imaged black holes in the galaxy M87 and in the galaxy NGC 3227. Eventually, they hope to image the black hole as well. Imaging it is challenging because it's much smaller on the sky than M87's black hole, despite being much closer. Sagittarius A also varies rapidly, changing on timescales of minutes. It's like trying to photograph a moving target that's constantly blurring. But the team is working on it, and an image would give us direct information about the black hole's environment. All these telescopes, working at different wavelengths, contribute pieces of the puzzle. No single instrument can tell the whole story. It's the combination of X-ray, gamma ray, radio, infrared, and optical observations that gives us the complete picture. There's also the role of computer simulations. We can't run experiments on galactic-scale structures. We can't create a supermassive black hole in a lab and watch what happens. But we can simulate them with supercomputers. Simulations model the physics of gas, gravity, magnetic fields, radiation, and particle acceleration. They let us test hypotheses. If we think the bubbles were created by a burst of black hole activity, we can set up a simulation with those initial conditions and see if it produces structures that match observations. These simulations are incredibly complex. The equations governing magnetized plasma interacting with radiation fields are nonlinear and coupled, meaning small changes can have big effects. Simulations require massive amounts of computing power, running for months on clusters of hundreds or thousands of processors. But they're essential. They let us explore scenarios we can't observe directly. They help us interpret observations by predicting what different physical processes should look like. And they guide future observations by telling us what to look for. The interplay between observation and theory is what drives progress. Observations reveal new structures like the structures. Theorists develop models to explain them. Those models make predictions. New observations test those predictions, refining the models. It's an iterative process, gradually converging on the truth. For all we've learned about these structures, there's still a lot we don't know. Let's talk about the biggest open questions. First, what exactly triggered the event that created the bubbles? Was it the black hole, a starburst, or both? And what specifically happened to trigger it? Did a gas cloud fall into Sagittarius A? Did a star get disrupted? Was there a gravitational perturbation from a passing satellite galaxy? We have ideas, but we don't have definitive answers. Second, how many times has this happened? Are the bubbles a one-time event, or are they the latest in a series of similar events stretching back billions of years? If it's cyclical, what's the period? Every few million years? Every few tens of millions of years? Understanding the cycle would tell us a lot about the long-term evolution of our galaxy. Third, what's the detailed structure inside the bubbles? We see them in X-rays and gamma rays, but what about other wavelengths? Are there clouds of cold gas embedded in the hot plasma? Are there regions of higher or lower density? How do the magnetic fields thread through the structure? Higher resolution observations at multiple wavelengths will help answer these questions. Fourth, how do the bubbles interact with the larger circumgalactic medium? The Milky Way is surrounded by a halo of hot gas extending hundreds of thousands of light years out. The structures are pushing into that halo. How does the interaction affect both structures? Does material from the bubbles mix into the halo, enriching it with metals from the galactic center? Or is there a boundary that prevents mixing? Fifth, what's happening at the boundaries? The sharp edges suggest ongoing processes, maybe shocks or particle acceleration. Can we detect those processes directly? Can we measure the acceleration of particles at the shock fronts? This would help us understand not just the bubbles, but the broader question of how cosmic rays are accelerated throughout the universe. Sixth, what will happen to the bubbles in the future? Will they continue expanding forever, gradually fading as the gas cools and disperses? Will they eventually merge with the circumgalactic halo? Or will something disrupt them, a new burst of activity from the black hole that creates a new set of bubbles within the old ones. Seventh, are there similar structures we haven't detected yet? The structures are perpendicular to the galactic plane, making them relatively easy to spot in our sky. But are there other, older structures at different angles or at different scales that we've missed? As our instruments improve, we might find additional layers of complexity. What do the bubbles tell us about the early universe? Supermassive black holes grew rapidly in the first few billion years after the Big Bang. Many of them likely went through active phases similar to what created these bubbles, but much more intense and prolonged. By understanding the physics in our own galaxy, we can better model what happened in those early galaxies, which are too distant for us to study in similar detail. Ninth, can we use the bubbles as a tool to study dark matter? The Milky Way's dark matter halo, the invisible mass that makes up most of the galaxy's mass, might interact with the bubbles in subtle ways. Some theories of dark matter predict that dark matter particles can collide and annihilate, producing gamma rays. The Fermi bubbles might be a place to look for this signature. So far, no definitive signal has been found, but researchers continue to search. How do the bubbles affect the evolution of the galaxy as a whole? They've removed gas from the central regions, reducing star formation there. But did they trigger star formation elsewhere, along their boundaries? Did they change the distribution of metals in the galaxy? Did they affect the overall rotation of the galaxy by redistributing angular momentum? These larger-scale effects are hard to measure, but they're important for understanding galactic evolution. Each of these questions represents an active area of research. Astronomers around the world are working on them, analyzing data, running simulations, proposing new observations. Science is an ongoing process, not a finished product. The structures are a discovery that's opened new questions, even as it answered old ones. Magnetic fields are invisible, but they play a crucial role in structures like the structures. Let's dig into how. The galactic magnetic field has structure. Near the disk, the field lines tend to spiral, following the spiral arms of the galaxy. Near the galactic center, the field is stronger and more chaotic, twisted by the differential rotation of the galaxy and by the various sources of energy in that crowded region. When the bubbles formed, they didn't just push gas around, they also pushed and stretched the magnetic field. Imagine pulling taffy. As you stretch it, the internal structure elongates. Magnetic fields behave similarly. The expanding bubbles stretched field lines from the galactic center outward, creating a draped structure. These stretched magnetic fields can resist further expansion, providing a confining pressure that helps maintain the bubble's shape. They can also prevent different regions of gas from mixing. Charged particles can easily move along field lines, but have a hard time crossing them. This creates barriers that can keep the hot gas inside the bubbles separated from the cooler gas outside. Magnetic fields are also crucial for particle acceleration. When magnetic field lines reconnect, rapidly rearranging themselves in a new configuration, they release energy. This energy can accelerate particles to very high speeds. Reconnection happens all the time in astrophysical plasmas, especially in regions with lots of turbulence and shocks. The edges of these structures, where the hot interior meets the cooler exterior, are natural sites for reconnection. Turbulence generated by the expanding bubble stirs the magnetic field, creating regions where field lines with opposite directions come close together. When they reconnect, particles get accelerated. These accelerated particles are what produce the gamma-ray emission we see with Fermi. When high-energy electrons interact with photons or magnetic fields, they can produce gamma rays. When protons interact with other particles, they can produce gamma rays indirectly through a chain of particle interactions. The magnetic fields are the engine driving this process. There's also a phenomenon called magnetic draping. When a fast-moving object moves through a magnetized plasma, the magnetic field lines bend around it, like water flowing around a rock in a stream. The structures are like a rock, and the galactic magnetic field is like the stream. The field drapes around the bubbles, creating a compressed layer at the boundaries. This draped field can amplify particle acceleration. The compressed field is stronger, which means particles spiraling around those field lines can reach higher energies. It also creates instabilities, ripples in the field that can scatter particles and accelerate them further. Measuring magnetic fields in space is challenging. We can't send probes to the galactic center to take measurements. Instead, we infer the field from its effects. One way is through polarization of light. Radio waves and optical light can be polarized, meaning the waves oscillate in a particular direction. When light passes through a magnetized region, the polarization can rotate. By measuring this rotation, called Faraday rotation, we can map the magnetic field. Radio telescopes have used Faraday rotation to map the magnetic field in and around the structures. The results show a complex structure with field lines that are generally aligned with the bubble's expansion, but with lots of small-scale tangling and variations. Another way to study magnetic fields is through synchrotron radiation. This is the radio emission from relativistic electrons spiraling around field lines. The intensity and polarization of this emission depend on the field strength and direction. By analyzing the synchrotron emission from the bubbles, we can learn about the magnetic field within them. The studies so far suggest that the magnetic field in the bubbles is strong enough to be dynamically important. It's not just a passive tracer of the gas. It's actively influencing how the gas moves, how particles are accelerated, and how the bubbles evolve. There's also speculation about the role of the black hole's spin in creating the magnetic field structure. Supermassive black holes can spin, and their spin affects the space-time around them. In a process called the Blandford-Znajek mechanism, a spinning black hole in a magnetic field can extract energy from its rotation and channel it into jets. If the black hole is spinning, and there's evidence it is, then its spin would have influenced the jets that created the bubbles. The jets would have been launched along the black hole's rotation axis, and the magnetic field would have been twisted by the rotation, creating a helical structure. We don't yet have direct measurements of the black hole's spin, but the structure of these bubbles might provide clues. If the bubbles show signs of helical magnetic fields, it would support the idea that the black hole's spin played a role in shaping them. Let's bring this back to Earth for a moment and talk about what the bubbles mean for us as humans living on a small planet in this galaxy. First, there's the sense of scale. We live in a galaxy that has structures tens of thousands of light years across, created by energies we can barely comprehend. It's humbling. Our entire recorded history, all of human civilization, is a blink of an eye compared to the timescales on which these bubbles formed. But it's also awe-inspiring. We're part of this. The atoms in our bodies were forged in stars, some of which might have contributed to the gas in the structures. We're made of the same stuff, governed by the same physics. We're not separate from the cosmos, we're embedded in it. Second, there's the realization that our galaxy is dynamic. It's easy to look at the night sky and think of it as unchanging, eternal. The stars look the same as they did for our ancestors thousands of years ago. But on longer timescales, everything is in motion, evolving, changing. The structures are evidence that the Milky Way has a violent side. Our neighborhood might be calm, but the galactic center is a different story, and that violence isn't destructive in a senseless way. It shapes the galaxy, regulates star formation, distributes elements throughout space. It's part of the cycle of cosmic creation. Third, there's the question of safety. Should we worry about the bubbles? The answer is no. The bubbles are far away, halfway across the galaxy. Even if they were pointed directly at us, which they're not, the effects on Earth would be negligible. The gas is incredibly thin, and by the time any high-energy particles reached us, they'd be diluted and scattered. But it does raise interesting questions about life elsewhere in the galaxy. If you were a planet orbiting a star near the galactic center, and these bubbles expanded through your neighborhood, would you be affected? Probably not much. The bubbles are mostly empty space with very dilute gas, but there might be an uptick in cosmic rays, high-energy particles that could pose a radiation risk. Life on such a planet might need better protection, thicker atmospheres, stronger magnetic fields, or life might not have arisen there in the first place if the conditions were too harsh. The galactic center is a crowded, energetic place. It might not be the best real estate for life. Our location in the galaxy, about halfway out in a relatively quiet spiral arm, might be ideal. We're far enough from the center to avoid the chaos, but close enough to benefit from the heavier elements created by generations of star formation. Fourth, there's the technological achievement. The fact that we can detect and study the bubbles at all is remarkable. We've built instruments that can see invisible light from across the galaxy. We've developed theories that let us interpret that light and understand the physics behind it. We've created simulations that model processes we'll never witness directly. This is human ingenuity at its best. A species that evolved on a single planet that only invented telescopes a few hundred years ago is now mapping structures spanning tens of thousands of light years and unraveling their origins. That's extraordinary. Fifth, there's the inspiration. Discoveries like these bubbles inspire new generations of scientists. A child today might see an image of these bubbles and decide they want to be an astronomer. They might grow up to make the next great discovery, to build the next great telescope, to solve the mysteries we're still grappling with. Science builds on itself. Each generation stands on the shoulders of the previous one, seeing a little further, understanding a little more. The structures are part of that ongoing story, a chapter in humanity's quest to understand the universe. And finally, there's the philosophical angle. The bubbles are a reminder that we're part of something larger. Our galaxy has a history, billions of years of evolution. The structures are a moment in that history, a brief flare-up of activity that will fade with time. But they left a mark, and we're here to read it. We're the universe's way of knowing itself, as Carl Sagan famously said. Through us, the cosmos examines its own structure, contemplates its own origins. The structures are a message from the past, written in X-rays and gamma rays, and we've learned to read it. What comes next in our study of these structures? Let's look ahead. First, more observations. The telescope continued its sky scans beyond the first four, building up an even deeper map. Each scan adds more data, improving the signal-to-noise ratio and revealing fainter structures. The team is analyzing this data now, and we can expect new results in the coming years. There are also other X-ray telescopes that can contribute. NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton are still operational. While they can't map the entire sky, like they can zoom in on specific regions of the bubbles at much higher resolution, this could reveal details about the temperature structure, the chemical composition, and the dynamics of the gas. The James Webb Space Telescope, humanity's newest and most powerful space telescope, operates in infrared wavelengths. It can't see the bubbles directly, but it can study the galactic center environment in unprecedented detail. By mapping the distribution of stars, gas, and dust, it can provide context for where the bubbles formed and what they're interacting with. With these next-generation instruments, we'll be able to study the bubbles in much greater detail, mapping their structure and looking for signs of particle acceleration at the boundaries. We might also detect fainter emission from the outer regions, further connecting different parts of the structures. On theory side, simulations are getting better. The next generation of supercomputers will be even more powerful, allowing for simulations that include more physics, higher resolution, and longer timescales. These simulations will help us test different models for the bubble's formation and evolution. Machine learning is also playing a role. Researchers are using neural networks to analyze the vast amounts of data from telescopes, identifying patterns that human eyes might miss. These techniques could reveal subtle structures within the bubbles or help us connect the bubbles to other features of the galactic center. There's also growing interest in multi-messenger astronomy, combining observations from different types of messengers, light at all wavelengths, cosmic rays, neutrinos, and even gravitational waves. While gravitational waves from the galactic center are probably too weak to detect, cosmic rays and neutrinos could provide new information about the high-energy processes in the bubbles. Neutrino detectors like IceCube, buried in the ice at the South Pole, are searching for neutrinos from astrophysical sources. Neutrinos are produced when very high-energy protons collide with other particles. If the bubbles contain such protons, they might produce a detectable neutrino signal. We're also learning to think about the structures in the context of galactic archaeology. Just as archaeologists reconstruct ancient civilizations from ruins, astronomers reconstruct galactic history from the structures we observe today. The structures are like ruins, evidence of a past event. By combining them with other evidence, like the distribution of stellar ages and chemical compositions near the galactic center, we can piece together a more complete history. And as we learn more about our own galaxy's bubbles, we'll use that knowledge to understand similar structures in other galaxies. Comparative studies will help us identify universal patterns and unique features, refining our theories of galaxy evolution. There's also potential for citizen science. The data from these observations and other telescopes is often made public after an initial proprietary period. Citizen scientists have contributed to astronomy in many ways, from classifying galaxies to discovering exoplanets. Perhaps volunteers will help analyze data from these bubbles, finding features that automated algorithms miss. Let's zoom out and think about what they tell us about the universe as a whole. Galaxies are the fundamental building blocks of the universe on large scales. There are hundreds of billions of them scattered throughout the observable universe. Each one is a complex ecosystem with stars, gas, dust, dark matter, and usually a supermassive black hole at the center. For a long time, astronomers thought of galaxies as relatively simple systems. Stars form from gas, live their lives, and die, returning material to space. The cycle repeats. The supermassive black hole sits at the center, growing slowly over time. But as our observations improved, we realized galaxies are far more dynamic. There are constant flows of material, inward and outward. Stars don't just form passively. Their formation is regulated by feedback from supernovae, stellar winds, and black hole activity. Galaxies merge, collide, and interact, triggering bursts of star formation or shutting it down entirely. The structures are a perfect example of this complexity. They're evidence that our galaxy's black hole isn't just sitting there passively growing. It's had bursts of activity that fundamentally reshaped the galactic center. And this probably wasn't a one-time event. It's likely happened multiple times over the galaxy's history. This fits into a broader picture of galaxy evolution. When galaxies are young and gas-rich, they form stars rapidly. Their supermassive black holes grow rapidly too, fed by abundant gas. The black holes produce jets and outflows, which blow gas out of the galaxy. This regulates star formation, preventing the galaxy from using up all its gas at once. Over time, as the gas is depleted, star formation slows. the galaxy transitions from a blue, star-forming galaxy to a red, passive galaxy. The supermassive black hole goes through cycles of activity, each one ejecting some gas but also clearing the way for future growth. The Milky Way is in a middle phase. We're still forming stars, but not as rapidly as we did billions of years ago. Sagittarius A is mostly quiet, but it has had active episodes, like the one that created the structures. In another few billion years, the Milky Way will merge with Andromeda, and that will trigger a new burst of star formation and black hole activity. The galaxy will be transformed. The structures are a snapshot of this ongoing evolution. They're a window into a process that happens throughout the universe, in galaxies big and small, from the earliest times to the present day. There's also a connection to cosmology, the study of the universe as a whole. The distribution of galaxies in the universe isn't random. They're arranged in a cosmic web, with clusters and filaments of galaxies separated by vast voids. This structure formed from tiny density fluctuations in the early universe, amplified by gravity over billions of years. Feedback from star formation and black holes plays a role in shaping this structure. If galaxies could turn all their gas into stars without any feedback, they'd be much more massive than observed. Feedback ejects gas, which can fall into nearby galaxies or remain in the space between galaxies, affecting how structure grows. These structures, by ejecting gas from the Milky Way, are contributing to the circumgalactic medium. That gas carries energy, momentum, and chemical elements. It might eventually fall back into the galaxy, or it might escape entirely, joining the intergalactic medium. Either way, it's part of the cycle that connects galaxies to the larger cosmic web. There's also a philosophical dimension. The universe is vast and old, and we're only just beginning to understand its workings. Every discovery, like these bubbles, is a reminder of how much we still don't know. It's humbling, but also exciting. There's always more to learn, always new mysteries to uncover. And finally, these bubbles remind us that the universe is active. It's not a static painting. It's a dynamic, evolving system. Stars are born and die. Galaxies grow and merge. Black holes feed and jet. And through it all, there's a beauty and complexity that's deeply compelling. We're lucky to live in a time when we have the technology to study these phenomena. A century ago, we didn't even know other galaxies existed. Now we're mapping structures tens of thousands of light years across in our own galaxy and studying similar structures in galaxies millions of light years away. The pace of discovery is staggering, and there's no sign it's slowing down. There's another fascinating aspect of these bubbles that we haven't explored yet. How do they interact with the rotation of our galaxy? Our galaxy isn't static, it's rotating, like a giant cosmic pinwheel. But it doesn't rotate like a solid disk. Different parts rotate at different speeds. Stars closer to the center orbit faster than stars further out. This is called differential rotation. The Sun, along with our entire solar system, is orbiting the galactic center at about 220 kilometers per second. At that speed, it takes us roughly 230 million years to complete one orbit. The last time we were at this same position, dinosaurs were just beginning to dominate Earth. When the bubbles were created, they didn't just expand outward. They also had to contend with this rotation. The gas being expelled from the galactic center was already rotating with the rest of the galaxy. As it got pushed outward, it carried that rotation with it. Think of it like a figure skater doing a spin. When they pull their arms in, they spin faster. When they extend their arms out, they spin slower. This is conservation of angular momentum. The same principle applies to the gas in the bubbles. As it moved outward, further from the galactic center, its rotation speed changed. This creates interesting effects in the structure of the bubbles. The gas doesn't just move straight out. It follows curved paths, influenced by both the outward push from the energy source and the rotational motion it inherited from the galactic center. Astronomers have looked for these signatures in the bubbles. Using the Doppler shift technique, they can measure not just how fast the bubbles are expanding outward, but also how fast different parts are moving in the rotational direction. The results show that the bubbles are indeed rotating, though more slowly than the gas at the galactic center. This tells us something important. The observations suggest there is some rotational motion, but it's not dominant. The expansion is the main component. This supports the idea that the bubbles were created by collimated jets shooting out along the black hole's rotation axis, which happens to be roughly aligned with the galaxy's rotation axis. There's also the question of how the bubbles affect the galaxy's rotation. When you remove millions of solar masses of gas from the galactic center and spread it over a huge volume, you're redistributing angular momentum. By pushing gas outward, the bubbles transferred angular momentum from the inner galaxy to the outer regions. The bubbles might also interact with the spiral arms of the Milky Way. Our galaxy has several prominent spiral arms where stars and gas are concentrated. These arms aren't solid structures. They're density waves, regions where material gets temporarily compressed as it orbits the galaxy. As the expanding bubbles push gas outward, they might encounter spiral arms at various distances from the center. These encounters could compress the gas in the arms, potentially triggering star formation. Or they might disrupt the arms, creating gaps or irregularities in the spiral structure. There's also the vertical structure of the galaxy to consider. Most of the stars and gas in the Milky Way are concentrated in a thin disk, only about 1,000 light-years thick. But the bubbles extend far above and below this thin disk, into regions that are usually much less dense. By pumping hot gas into these regions, the bubbles are changing the vertical structure of the galaxy. They're making the halo thicker, at least temporarily, and they're influencing the pressure balance between the disk and the halo. This pressure balance is important for regulating star formation in the disk. The bubbles are part of this regulatory system. They're one of the mechanisms that keeps the galaxy in balance, preventing it from turning all its gas into stars too quickly or too slowly. It's a delicate equilibrium, and understanding how all the pieces fit together is one of the grand challenges of galactic astronomy. We've talked about seeing these bubbles in X-rays and gamma rays, but there's much more to the story when we look at them across the entire electromagnetic spectrum. Each wavelength reveals different aspects of these structures. Let's start with radio waves. Radio observations reveal something the X-ray and gamma ray observations don't show as clearly: the magnetic field structure. When relativistic electrons spiral around magnetic field lines, they emit radio waves in a process called synchrotron radiation. The polarization of these radio waves tells us about the orientation of the magnetic field. Radio telescopes have mapped these polarized emissions across the bubbles, revealing a complex web of magnetic fields. Some field lines run parallel to the bubble walls. Others are more tangled, showing regions where the field has been twisted by turbulence. The radio observations also show us the total energy in relativistic particles. By measuring the brightness of the radio emission and knowing the strength of the magnetic field, we can calculate how many high-energy electrons are present and how much energy they carry. Moving up in energy, we come to infrared light. Infrared telescopes can't see the hot gas in the bubbles directly, but they reveal something else important: dust. There are dust clouds associated with the bubbles, particularly at the boundaries where the expanding bubbles are sweeping up material. This dust tells us about cooler material mixed in with the hot gas. The bubbles aren't filled exclusively with million-degree plasma. There are also cooler clouds mixed throughout. The infrared observations also help us understand star formation triggered by the bubbles. Young stars forming at the bubble boundaries would be embedded in thick cocoons of dust. Infrared light can penetrate this dust, revealing hidden stellar nurseries. Optical observations show filaments of ionized gas throughout the bubble region that glow in specific wavelengths. One particularly important emission line is hydrogen alpha, the red light emitted by hydrogen atoms. This traces warm ionized gas at around 10,000 degrees, much cooler than the million-degree gas emitting X-rays. This warm gas forms a transition layer between the hot interior and the cool surrounding medium. Ultraviolet observations add another piece. The Galaxy Evolution Explorer satellite mapped ultraviolet emission from the bubble region and found evidence of both star formation and hot gas halos around the bubbles. The ultraviolet observations also revealed absorption features. When we look at distant bright objects through the bubbles, atoms in the bubble gas absorb specific wavelengths, leaving dark lines in the spectrum. Beyond gamma rays, very high-energy gamma rays require ground-based telescopes. These detect the cascades of particles created when extremely energetic gamma rays hit Earth's atmosphere. Several observatories have looked at the bubble region and found very high energy emission, particularly from the boundary regions. This tells us that particles are being accelerated to truly extreme energies. What about neutrinos? Neutrinos are ghostly particles produced in some of the same processes that create gamma rays. The IceCube neutrino detector in Antarctica has been searching for neutrinos from the bubble direction. So far, no clear detection, but the search continues. A definitive neutrino signal would confirm that protons are being accelerated to extreme energies. All these different wavelengths together tell a rich story. The bubbles have hot gas emitting X-rays, relativistic particles producing gamma rays and radio waves, dust and cooler gas visible in infrared and optical light, and extremely energetic processes at the boundaries. It's like examining a painting under different types of light. Each wavelength reveals hidden aspects of the bubbles, and only by combining all these views do we get the complete picture. This multi-wavelength approach is the future of astronomy. No single telescope can tell the whole story, but by coordinating observations across the spectrum, we can build comprehensive models of complex structures like these bubbles. So let's bring this all together. The structures are two enormous structures extending 50,000 light-years above and below the Milky Way's center. They're filled with hot gas at millions of degrees, emitting X-rays that we can detect with specialized telescopes in space. These bubbles were likely created a few million years ago by a burst of activity from the black hole, the supermassive black hole at our galaxy's center. That activity produced jets, powerful outflows that plowed through the surrounding interstellar medium, creating the bubbles we see today. The bubbles are connected to the Fermy bubbles, similar structures detected in gamma rays. Together, they paint a picture of our galaxy's violent recent past. They tell us that the Milky Way's center isn't always the quiet place it appears to be today. Studying the bubbles teaches us about supermassive black holes, about galactic feedback, about the cycle of star formation and the distribution of elements. They're a laboratory for understanding processes that happen throughout the universe. We've learned a lot in the few years since the bubbles were discovered, but many questions remain. What exactly triggered the event that created them? How often does this happen? What's the detailed structure inside the bubbles? How do they affect the galaxy's evolution? Answering these questions will require more observations, better simulations, and creative thinking. It will require new telescopes and new techniques, but that's what science is all about. It's an ongoing journey, not a destination. And as we continue to study these bubbles, we'll not only learn about our own galaxy, but about galaxies across the universe. we'll understand how feedback shapes galaxy evolution. We'll see how supermassive black holes and their host galaxies co-evolve. We'll piece together the cosmic history that led to the universe we see today. The invisible bubbles shaping everything in the Milky Way's center are no longer quite so invisible. We've seen them, measured them, and begun to understand them. But they still hold secrets, and uncovering those secrets will be one of the great adventures of 21st century astronomy. Look up at the night sky tonight. You won't see these bubbles with your eyes. They're invisible in the light our eyes can detect. But they're there, enormous structures filled with superheated gas and high-energy particles, monuments to a time when the heart of our galaxy was far more active than it is today. They're a reminder that our galaxy has a history, a story written in gas and stars and light. And we're privileged to be the ones reading that story, deciphering its meaning and sharing it with the world. The universe is full of wonders, and these bubbles are among the most spectacular. They're vast, energetic, and mysterious. They challenge our understanding and inspire our curiosity. And they're just one discovery among many that await us as we continue to explore the cosmos. Thank you for joining me on this journey through the invisible structures shaping our galaxy. The structures are out there, right now, expanding ever so slowly into space. And thanks to the work of dedicated scientists and engineers around the world, we can see them, study them, and marvel at them. The universe is an incredible place, and we're only beginning to understand its secrets. But every discovery brings us closer to a complete picture of how everything works, from the smallest particles to the largest structures. The structures are part of that picture, a crucial piece of the puzzle. And as we continue to study them, we'll unlock new knowledge, answer old questions, and inevitably uncover new mysteries. That's the beauty of science. The more we learn, the more we realize there is to learn. The journey never ends, and that's exactly how it should be.